Hello, I am Dr. Sudha from Government Science College, Autonomous, Bengaluru. In this session, let us discuss about the differential equations which are reducible to exact differential equations. We all know that a differential equation which is not exact can be made exact by multiplying by a suitable factor called an integrating factor. We have discussed about the rules for finding integrating factors of the equation 𝑀𝑑𝑥 plus 𝑁𝑑𝑦 equal to 0 by inspection as well as for an homogeneous equation in the previous sessions. In this session, let us discuss about the integrating factor for an equation of the type f1 of x comma y into y dx plus f2 of x comma y into x dy equal to 0. Let us find the rule for finding an integrating factor for an equation of the type f1 of x comma y into x dx plus f2 of x comma y into x dy equal to 0. If the equation 𝑀𝑑𝑥 plus 𝑁𝑑𝑦 equal to 0 is of the form as set in the above, that is f1 of x comma y into y dx plus f2 of x comma y into x dy equal to 0, then 1 over mx minus ny is an integrating factor provided mx minus ny is not equal to 0. So if we have an equation of this type, if mx minus ny is not equal to 0, then 1 over mx minus ny is the integrating factor, and we can consider this integrating factor, multiply the equation by this factor, that is 1 over mx minus ny, and make the equation exact and solve the equation using the method for solving an exact differential equation. Let us discuss some examples of this type. Consider the first example. Solve 1 plus xy into y dx plus 1 minus xy into x dy equal to 0. So let us look into the solution now. So let us consider the given equation, which is of the form f1 of x comma y into y dx plus f2 of x comma y into x dy equal to 0. Here we can see that m is 1 plus xy into y and n is 1 minus xy into x. Let us calculate what is mx and ny. So mx is 1 plus xy into yx and ny is 1 minus xy into xy. So consider mx minus ny, and that will be equal to xy plus x square y square minus xy plus x square y square. So here we can see that xy gets cancelled with this minus xy and gives us 2 times x square y square. And this is not equal to 0. That is mx minus ny is not equal to 0. Therefore, 1 over mx minus ny, and that is equal to 1 over 2x square y square, is an integrating factor for this given differential equation. Let us multiply the given differential equation by this integrating factor to get 1 over 2x square y square into 1 plus xy into y dx plus 1 over 2x square y square into 1 minus xy into x dy equal to 0, and this becomes exact. So let us simplify this to get 1 over 2x square y plus 1 by 2x into dx plus 1 over 2x y square minus 1 over 2y into dy equal to 0, and this is a exact equation because we multiplied the given equation by the integrating factor to get an exact differential equation. And we know that exact differential equation, the solution is obtained by the equation integral m dx where y is kept constant plus integral terms of n not containing x into dy equal to c. Here this m is this new m obtained here and n is this new n which is obtained after multiplying the equation by the integrating factor. So now let us substitute for m and consider the terms of n not containing x. So in this term, the first term is containing the variable x. So we need to neglect this term. We need to consider minus 1 over 2y which is independent of x. So we get integral 1 over 2x square y plus 1 over 2x keeping y constant plus integral minus 1 by 2y dy equal to c, where c is the constant of integration. Now let us integrate both the integrals and we get 1 over 2y which is a constant kept as it is. 1 by x square gives us minus 1 by x plus half into 1 by x gives us log x minus half into 1 by y gives us log y equal to c. Now we can remove half common throughout on the left hand side and we can combine these two logarithmic terms together to get 1 by 2 into minus 1 by xy plus log of x by y equal to c. Here you can cross multiply this 2 to the right hand side and write this expression as log x by y minus 1 by xy equal to 2c. And this is the solution to the given differential equation. Now let us consider or discuss one more example wherein we have trigonometric functions. Solve xy into sine of xy plus cos of xy into y dx plus xy into sine of xy minus cos xy into x dy equal to 0. So let us consider the solution now. So consider the given differential equation which is of the form f1 of x comma y into y dx plus f2 of x comma y into x dy equal to 0. Here we can see that m is xy sin xy plus cos xy into y and n is xy into sine of xy minus cos of xy into x. Now let us calculate what is mx and ny. So mx is xy sin xy plus cos xy into yx and ny is xy into sine of xy minus cos of xy into xy. Now let us consider mx minus ny. So this gives us x square y square sin xy plus xy into cos of xy minus x square y square sin xy plus xy into cos xy. Here we can see that this first term, that is x square y square sin xy, and the third term minus x square y square into sine of xy gets cancelled and it gives us 2 times xy cos xy, and this is not equal to 0. Therefore 1 over mx minus ny equal to 1 over 2xy into cos of xy is the integrating factor to the given differential equation. So let us multiply the given differential equation by the integrating factor 1 over 2xy into cos of xy to get 1 over 2xy into cos of xy into xy into sine of xy plus cos of xy into y dx plus 1 over 2xy into cos of xy into xy into sine of xy minus cos of xy into x dy equal to 0. And this is exact after multiplying by the integrating factor. So let us simplify this now to get y tan of xy by 2. From the first term we get sine of xy divided by cos of xy, that gives us tan of xy, and x gets cancelled here as well as y gets cancelled here, leaving y tan of xy by 2 plus 1 over 2x. And from the second term, we get x tan of xy by 2 minus 1 over 2y dy equal to 0. Now this is the differential equation obtained after multiplying by the integrating factor, and this is exact. And we all know that the exact differential equation, after simplification, that is removing half common throughout, we get this, and now we can multiply this half to the right hand side. So 2 into 0 gives us 0. So we get y tan of xy plus 1 over x into dx plus x tan xy minus 1 by y into dy equal to 0. And this is exact now, and the solution is given by integral m dx plus terms of n not containing x into dy equal to c, where c is the constant of integration. Here we need to remember that m and n are the factors of dx and dy obtained after multiplying by the integrating factor. So let us substitute for m, that is y tan of xy plus 1 by x into dx, keeping y constant, plus integral minus 1 by y dy equal to c. Now let us integrate the first integral, keeping y constant. So here in the first term, y into tan of xy. So y is constant, and we know that integral of tan is log secant. So y is kept as it is, log of secant of x into y, and the coefficient of x is here y, so divide by y, plus 1 by x gives us log x, minus 1 by y gives us log y equal to c. And this is the solution to the given differential equation. Here one can cancel out this y, and you can write log secant xy plus log x minus log y equal to c. And also we can combine all the logarithmic terms and write the solution. Thank you.